Hey everybody, Gianmarc here today with a lesson on time correlation functions. So this one is a purely mathematical one, although there are applications to music. Let's talk about the motivation here. Why would we want to study time correlation functions? So let's first think about some sort of observable. And this observable is going to be a function of a random variable x, and it's going to change over time. So just for to give some concrete example, let's say a weather vane on the roof of a house. Sorry, my dog just sneezed. Let's say there's a weather vane on the roof of a house, and the wind blowing could be our random variable. So you don't know what direction the wind is going to blow, and that's our random variable. And we measure, let's say, the direction that the weather vane is pointing. So that could be our A, is measuring the direction of the weather vane. And then if we make two consecutive measurements with some gap in time in between, some sort of delay, then that delay is t. So if we measure the direction and then measure it again a millisecond later, we're probably going to get almost the exact same value in both measurements, right? Because the weather vane typically on the order of milliseconds hasn't moved very far. So for our time correlation with a 1 millisecond gap, we're going to have high correlation. But then let's say we look at measurements that are a month apart. Well, then now you might see almost no correlation in the direction unless you happen to live in an area where the wind blows in a pretty consistent direction. And that's something a time correlation function could show you. If you still had strong correlation on measurements made a month apart, then you could say, yeah, the wind blows in a pretty consistent direction here. So of course not too many people are using it for weather vanes, but there's lots of applications within spectroscopy, which is an area of physical chemistry, and also signal processing. So just to bring up an example involving music, since I usually do videos with music stuff, say you could cue in on the amount of times that the frequency spectrum of a recording peaks in a certain range. So say like when the snare drum hits, there's certain frequencies that are going to get really high at a certain point. So if you were able to use time correlation functions to figure out how far apart those hits are, most typically, then you'd be able to figure out the tempo. So there's a music example. All right. And also just a few things to specify. Time correlation functions are also called autocorrelation function, since if you assuming that you're measuring the same thing multiple times, right? So you could do correlation functions between two different observables, like the direction of the weather vane and I don't know, the temperature outside or something. But if you're looking at measurements of the same system of the same type with different time gaps, then it's an autocorrelation function. And also we're going to be doing absolute time correlation functions. So here's an example of a data set that we could generate that where a time correlation function could come in handy. So essentially it's a sine wave, right? So you can see the formulas right here. Alright, so it's a sine wave, but I've added this noise to it. And end strength is the strength of the noise. So you can see here we have the amplitude of the sine wave dropping the stronger the strength gets. And here is our random kicks that we're giving to our system. That instead of just saying as a normal sine wave, it's going to be a sine wave plus or minus some random number we're going to draw between -1 and 1 multiplied by the strength. So best way to get a feel for this is just to look at a plot. So if I set the end strength down to 0, then you see it's a normal sine wave. But now if I allow end strength to get a little stronger, you can see how our sine wave is getting fuzzier and fuzzier. All right, it's getting noisier and noisier. It's less of a pure sine wave the stronger I make this. So now if I get this thing up to like 96% or 0.96 for my end strength, and end strength doesn't go any higher than 1 for this model, we can look at this and yeah, you can kind of maybe make out that there might be a sine wave in there. But if all you were given was this data, and I asked you what function's in there, I don't know if anyone would want to bet money that there's a sine wave buried in that. But a time correlation function can dig that out for us and let us know if there's anything going on in a correlated way there. Oh, also, one way to talk about this is memory. You can say how long is the system's memory. So again, going back to that weather vane example, we'd have high correlation if we measured its direction. If we make two measurements a millisecond apart, right? They're going to be very similar measurements. So we could say that within a millisecond, there's very good memory for that system. But then if we make measurements a month apart, then if you don't see like any correlation there or very weak correlation, you could say that the memory is it's forgotten where it was by the time a month goes by. So another way to think about time correlation functions is how long is the system's memory. So you have these random systems that aren't completely random, and you want to know how long their memory is. Okay, so let's start with a little bit of a derivation, but not really. So here's the formula for a time correlation function right here. So this is the typical formula you'll see. And essentially it's two measurements, right? A is making our measurement of our system that depends on some random variable x. And t here is the delay between the delay that we wait before we make the measurements. So if we set t to equal to 0, that means an instantaneous measurement. So if we measure it once right away and then again, we measure it again with a delay time t, that's what these two measurements are. And then it's multiplied by f of x. So f of x is just the probability distribution function of our random variable x. If you're not familiar with probability distribution functions, then that might be something good to look up, and I'm actually probably going to do a video on that myself later, so I'll put a link as soon as I do here. So anyway, if you're looking at some sort of random variable that is predicted by some sort of probability distribution function, f of x, then if you wanted to take the mean of it, then you just integrate x times f of x. That's all you need to do with respect to x. If you've taken quantum mechanics, that might look kind of familiar, except you'd have an x in the middle of a bra and a ket. But it's essentially the same thing. So let's see here. And likewise, if we wanted to take the variance, that would be x squared times f of x, and then you integrate. So this is just standard procedure for figuring out mean or variance if you're given some continuous probability distribution function f of x. So now to generalize this, let's say we want to take the variance of our observable, assuming that there's 0 time delay between the measurements. So if we want to figure out the variance of our measurements of just, you could think of it as 2 measurements with 0 time in between, or just taking one measurement and squaring it. It's probably a simpler way to think about it. So if we do that, then that's taking the variance of this, right? And if we look at that, it's getting really close to our definition of a time correlation function. So we're getting there. So now, instead of saying that both of them are 0 time delay, let's introduce time delay into one of these a's and leave it as a parameter. So if you notice that we now have our time correlation function. And so if you were to perform this integral here, you'd notice that x gets integrated out. We're integrating with respect to x, right? So x is gone after you do this integral, but t persists. So that's why c is a function of t. So this is essentially our time correlation function. So it's almost like taking a variance, but allowing some time delay in between measurements. In fact, if you look at c of 0, so if c of t equals 0, it is the variance of A. So if you were to do a plot of C of t, the first point at C of 0 should be the variance of A for these absolute time correlation functions. Let's see. So it's also worth noting that the more concise notation that you'll often see for this will just be C of t is the expectation value of A of t times A of 0. So this is more what you see in the literature and stuff. So I feel this form is more informative to look at. But if you know what you're looking at when you look at expectation values, like the notation, then you'll see that these really are equivalent. But that's why I wanted to start with this notation just because I thought it was more informative. But typically, this is the one that you'll see in literature and stuff. Okay, so now we've pretty rigorously defined what a time correlation function is when it comes to continuous probability distributions of continuous functions of of random variables. So we've got functions of random variables that continuously vary over time. But now let's talk about a numerical approximation to this. Because if you want to look at a physical system, you're typically not making continuous measurements, right? Like particularly anything digital. For example, let's just keep using that weather vane example. If I have some sort of detector up there that can measure the angle, and then I'm using a computer to control that, and I'm measuring the angle every, whatever time gap that I've specified, t, then we're going to get discrete values of direction, and each time step is going to be the same discrete time step. So it's not continuous now. Now it's discrete. And something you'll see a lot in physics is taking integrals and representing them as summations. And that's what we're doing here. So our time correlation function C of t, we're expressing it as a summation instead of an integral here. And if you look at it, it kind of makes sense in terms of our variance. So let's first look at this and think about what a variance is. So if I set t equal to 0, then we just have a naught times a naught. So we're squaring our measurement for all of our measurements. And then our summation is going to go from I to n. And we're going to add all those up. And then we're going to divide by n, right? Because t is 0 for the 0 point. For C of 0. So then essentially that's our time correlation function, right? That's how you take the variance of this. So I think the easiest thing is to just look at a very, very simple data set here. So let's say I make only 4 measurements, not typically a data set of 4 you wouldn't bother of n equals 4 you wouldn't bother with a time correlation function, but it's good for learning. So let's say at 0 time I make a measurement A. At time step 1 I measure B. Time steps did I start the counting at 0? I forget how I counted it. Well, anyway, so we're at these discrete time steps we're making a measurement, and the answers we get are A, B, C, and D. Right? So we have 4 measurements, so n equals 4. So C of 0 is going to be 1 over 4 times A squared plus B squared plus C squared plus D squared. I don't know why it changed to the partial differentiation D, but that's just a D squared. And then when we have a C of 1, so our time correlation function at time equals 1, t equals 1, is just going to be, so now you're going to have a one time step delay between each thing. So instead of having a 0 time step delay where we're just going A squared, B squared, C squared, D squared, now we're going A times B, B times C, C times D. And then you divide that by 1 over n minus t, so that's going to give you 1 over 3. And you see that we're just taking an average. And again, for the last one, we got A times C, B times D. And then we take the average of that. So this is how you take the absolute time correlation function numerically. So now let's do an example with this. So that noisy sine function that I defined at the beginning of the lesson, remember I have that n strength value, which essentially determines how strong or how noisy our sine function gets. So here I have n strength set to 0.7, and if we look at a plot of it, you can see that, yeah, it still looks roughly like a sine function, but it is very noisy. So if I'm trying to figure out the memory of this, that means I'm trying to figure out that if I make some measurement and then another measurement a given number of time steps later, how well am I going to be able to predict what that second measurement is if I know what the first one is? Or in other words, how long is the memory of this particular system? So now we're talking about the memory of our noisy sine function with n strength 0.7. Okay, so here I have plotted the time correlation function. You can program it yourself using that numerical representation that I showed on the earlier slide. But Mathematica actually has a built-in function called absolute correlation function, which is the one I'm using here. So all you have to do is feed it your data and how long you want t to be, and it will calculate time correlation function. So that would be 1 point on this particular plot here. Okay, so looking at our time correlation function for noisy sine with n strength 0.7, what I have shown here is this top blue line is the variance of our 2000 measurements, and the red line here is the mean. So now, of course, with the sine function, you'd expect the mean to equal 0, and you notice that it's slightly more, but remember we have some random noise in there, and we've only gone for 2000 time steps. So you could call this an undersampled system, right? If I ran 2 million time steps, you know that red line would be almost exactly equal to 0. So let's see here. So here's our time correlation function, just going from c of 0 to c of t, and you notice it's dropping quite quickly, but hasn't yet gone as far as it'll go. The important thing to remember with this absolute correlation function is that it starts at the variance and will decay to the mean. I'm going to say that again because it's really important. It starts at the variance at with 0 time step, or with 0 delay time t, and as that delay time keeps going up, it will decay to the mean value. So if your time correlation function has decayed to the mean value, you know the correlation is over, like there's no correlation left. So let's go out a little further. Let's go 11 time steps. So 11 time steps, you see there's the initial decay, and then there's still some correlation left. It hasn't reached the mean. Let's take it one step further. 111 time steps. Seems like it's getting closer to the mean value. Let's go 1,111 steps. Okay, now we see some interesting behavior. Now we see that our absolute time correlation function here is it's behaving kind of like a damped oscillator, right? It's oscillating, but it's a decaying amplitude. You see how the amplitude here is smaller than here, and this one's smaller than that one. So it seems that it's decaying. And let's go a little further out. So now we've taken it as far as we can with this particular data set, and we see that our absolute time correlation function has decayed more and more, and then out by 2,000 time steps, it's practically at the mean. It's just about there. So this kind of shows that if we set n strength equal to 0.7, essentially there's very little time correlation left by the time if you make two measurements 2,000 time steps apart. All right, so that at that point, I mean before that too, it's already a pretty small correlation, but you won't really be able to predict the second measurement if you make two measurements 2,000 time steps apart. You're essentially at the mercy of the random piece, not the deterministic sign piece of the function, right? So that's that. Let's try it again, but this time we're going to make our noisy sine function using n strength equal to 0.9. So now we've made it even noisier. The last one was just 0.7. Now it's up to 0.9. And looking at this data, I mean, you might never guess there's a sine function buried in there if this was the only thing you had, if this was some measurement you made. So now we have it for 0.9. Okay, and for this one, going from time step 0, so going from two measurements made at the exact same time to two measurements made one time step apart, now it looks like, it actually looks like we've already reached the mean, right? So let's zoom out a little bit more. Okay, it seems if we look closely now, it's actually oscillating a little bit. So it hasn't quite relaxed all the way down to the mean value. Okay, so now we see it's still fluctuating about the mean. And it's at this point it seems to be fluctuating pretty evenly about the mean. Go a little further. Okay, now seeing it from this time frame, you can almost see some slight oscillation going on there. But let's go as far as we can take this particular data set of 2,000 measurements. And okay, now we look at it, and you'll notice that this sort of noise, this noisy fluctuations about the mean, are decaying. So even though we have very little correlation with this one, we can actually still see a difference between the correlation at, say, 2,000 time steps, measurements made 2,000 time steps apart versus, say, like 100 or something. You'll notice that the fluctuations about the mean are getting much smaller. So even with that, we could still make some sort of statement as to the memory that this system holds, even though it is very noisy. So hopefully this helped you understand time correlation functions a little bit. I know there's not a whole lot of stuff online. I didn't find much when I was trying to learn about them, so hopefully this sort of fills that gap. And thanks a lot for watching. Please subscribe, and if there's anyone you know who would watch this as well, then please share it with them. All right, thanks a lot.